Swayam Prabha. Digital India. Educated India.
A piecewise linear representation of a shape. So the first guess could be, representing a circle using a triangle. But we all know that that is a bad representation because you can see that there is this error between the circle and the triangle, which is, you know, it's glaringly a lot of error, a very large error between the circle area and the triangle area. So what can we do? Well, we know that we are free to use any polygon, right? So we can increase the number of sides of this polygon, let's say to 6, and then we see if this hexagon better represents this circle. Well, yes, to some extent we could say, yeah, it's a better representation of a circle, but then we could probably do better if we increase the size to 12. And with 12 also, you see a little bit of an error. So you increase it to 24, and then you can keep doing that. And you would notice that the more the number of sides you use of a polygon, the better your representation becomes, the closer it becomes to the circle. So the takeaway is that you can represent an arbitrary shape using with a piecewise linear representation. And in this case, the piecewise linear representation is my polyline representation, right? Which is a closed, so it becomes a polygon. But it's essentially a polyline representation as far as the boundary of the shape is concerned. And we are mostly concerned, in this case, we are mostly concerned about the boundary, because I'll come to surface meshes that are also boundary of a solid mesh, right? We'll talk about solid mesh and surface mesh in a bit. But a surface mesh, a surface is the boundary of a solid. So think of a wooden log, right? It's a solid mass. Most of the times, what we do is we just represent the boundary of that, the surface of an object. In this case, a wooden log, right? Because the interior of that you can't anyway see. So if your application doesn't demand analyzing or looking inside the wooden log, you don't want to represent it. Okay, so you just represent the boundary, which is the surface, and you're done. So that is a surface representation. So what could you do to do that? If it's a 3D object, you could just cover the surface of that wooden log with a set of triangles, right? Analogously, in this case, you have a disk. And what is the boundary of a disk? It's a circle, right? So you want to then cover the entire circle with a number of line segments, or a polyline in collection that best describes my circle. There is always an inherent error in this type of representation, and that error turns out to be order h square, where h is my distance, perpendicular distance between the line, the maximum perpendicular distance between the line segment and the circle, right? So that's my piecewise linear approximation in 2D, right? Which is known as a mesh. And in 3D or in 3 space, what I want to do is represent the boundary, cover the boundary. Whenever I say boundary, a boundary is defined in an n-dimensional space. And let's also go one step back and talk about the dimensionality of an object versus dimensionality of space. It's a small concept, but it goes a long way, because otherwise I have seen, we get confused between the dimension of the object and dimension of the space, right? So what is dimension of an object? The dimension of an object is its dimensionality. For example, a curve, a wire-like object, is always one-dimensional. A point is always zero-dimensional, irrespective of whichever space it is placed in, right? So if a point is placed in a 2D space, so if I draw a dot on a piece of paper, the point is still zero-dimensional, but the ambient space or the embedding space is 2-dimensional. So in this case, we would say the dimensionality of a space is 2, whereas the dimensionality of the object, which is a point, is 0. Similarly, for curves, they're always one-dimensional, be it drawn on a real line or drawn in a 2D space, or it's a 3D curve. Can somebody give me an example of a 3D curve? Anyone?
Sir,
A
helix.
helix? Yeah, great. A helix, right? A helix, a 3D helix is an example of a 3D curve. And similarly, you can go to higher dimensions. But a helix, for example, will always remain a one-dimensional object irrespective of the dimension it is placed in or embedded in. So similarly, if I say a surface, a 2D surface, I mean a sheet of paper. I can place a sheet of paper in a 3D space, but the sheet of paper will still remain a sheet of paper. If you zoom into any part of that sheet of paper, you will always notice that in the small vicinity, small surrounding of a point, it looks like a plane, two-dimensional space, even though globally it could be curved, right? So if an ant, for example, moves on a piece of paper which is, bent into a cylinder or something, the ant will not see the cylinder. It will always see that it is walking on a plain sheet, similar to what we observed, right? We see that the Earth is flat because locally speaking, the Earth looks like a plane everywhere, but globally it's like a body. It's a sphere. It's not spherical, but so the point here is that dimensionality of an object could be lower than the dimensionality of the space. I can embed for example, in the 3D space, I can always embed any object that is of dimension 3 or less. I can have solids in 3D space. I can have surfaces in 3D space, curves in 3D space, and points in 3D space, right? So that's the dimensionality of the embedding space versus dimensionality of the object. So when I say boundary of a shape, I mean the boundary as in the part of the shape which is on the outside, which is always one dimension less than the dimensionality of the shape. For example, if I have a ball, a solid ball, right, something that is filled inside, the boundary of that ball is going to be a sphere, a hollow one, right? And then I can, of course, a ball, a 3 ball stays in a 3 space as a solid ball, and I can always have this sheet, this sphere in that 3 space. So it is clear the dimensionality of the space versus the dimensionality of the object. And whenever I say boundary is a concept that can be that is defined in any dimensional space. When I say surface is usually referred to as a 2D shape, a 2D surface, right? So in this case, the boundary is a curve because it's a circle. But when I say a surface or a boundary of a solid, that's my 2D surface. So coming back here, and by the way, any questions, please shoot, please ask us right away. Now,
So just like clarifying again from whatever you discussed just now. So say we have just the boundary of the circle versus a disk. The boundary of the circle is a 1D object, whereas the disk is 2D.
The disk, yeah, that's right. So you don't say
Despite
boundary of
it
a
being
circle, you say boundary of a disk, because circle is anyway a one-dimensional object. So boundary of a one-dimensional object is going to be a point, which circle is a closed shape, so it may not have a boundary. Anyway, so you are right. In a sense, you said a disk. A disk is a 2D shape. It's a two manifold. A disk is a 2D
this
shape, and then a
no, not
circle is
regarding
a
the disk.
curve.
Yeah, regarding the circle, I wanted to ask. So, despite it being closed, we are considering it as one.
Yeah, so shapes could be closed, and that doesn't change. That may have no impact on its dimensionality.
Okay, thank you.
It could be open. I can cut it open and make it an open curve. In that case, it has a boundary. But if it's a closed curve, then there is no boundary. Similarly, you may have the same ideas in for surface meshes could be closed or open. If it's an open, you can find a boundary, but if it is closed, then no boundary. Right? Does it
Yes. Yeah.
okay. All right, great. So then we define a mesh as a graph. A mesh is a graph because it has two things. It has a connectivity and it has a geometry, right? So maybe now is the right time for me to write something. Let me share my screen quickly. Right. So a mesh. So what is a mesh? A mesh is a graph basically. Is a graph that has vertices and edges. It's a connectivity, right? So you have nodes connected with edges. But it's a special type of graph. It's a graph that has a lot of cycles. Because when I want to represent a shape, so for a shape, I need a tiling, right? So this is a tiling. What do I mean by a tiling? Is that the space is covered. So that's one tile, and then adjacent to it is another tile, then another tile, another tile, and another tile. And let's say that was my shape was the one I'm drawing in red here. That was my shape, let's say. Okay. So I could tile it with these polygons, let's say. Okay. And then for time being, let's just say that it's a 2D shape in 2D space. I can do that. We'll come back to 2D shapes in 3D space, but for now, let it be a 2D shape in 2D space, and I'm covering it with some polygons. So it's a tiling. Tiling, right? Tiling is important here. So how could I represent? There are clearly two things here. One is the topology of this tiling, and the other is the geometry of this tiling, right? So the topology is captured by a graph, and of course geometry is captured by the coordinates of the nodes or the vertices, right? So I can write here the coordinates of the vertices. So what kind of a graph is it? So when I said I tile it up, I have polygons here, and these polygons are connected to each other. So I'm just drawing it in between the vertices here, and there is some connectivity information which is stored here. Just draw thick lines. So these are this is the connectivity information. So that's my graph. That's my graph, right? So how can you store this connectivity information? This is best stored as a graph. That is, which node is connected to which other node. Make sense, right? So it's a graph that has a lot of cycles. There are no dangling edges, no dangling vertices, and so it's never a tree. It has all cycles, and it is these cycles that form the facets. So a mesh, I can say, is a graph with facets. Facets are essentially cycles, right? So a graph with facets where you have these edges that are connected to form facets. So what are the components of this graph? It has vertices, of course. It has edges that connect vertices, and then it has facets. Okay, so that's a mesh, and depending on what types of facets we have different types of meshes. For example, we may have triangle facets. We may have triangles here. In that case, it's known as a triangle mesh. We may have quadrilaterals, in which case it is known as a quad mesh. And in general, you can have any polygon, in which case it is known as a polygon mesh, a generalized polygon mesh. Some of the things, some of the I wouldn't say properties, but some of the obvious properties is that an edge always connects two vertices. I'll number them. An edge is incident on two facets always, right? These two are true always. And what else can I say here is that a vertex is connected to a number of edges, and this is known as the valence of the vertex. Known as the valence of the vertex. Okay, and of course, a facet has a number of edges, also known as sides of the facet, and also has a number of vertices, right? So that's pretty much it about a mesh. So these two, right? The number one and number two are always true and fixed. So an edge is always connected to two vertices, and an edge is always incident to two faces, right? And this is equivalent to saying that adjacent faces share an edge. I hope that's clear. So yeah, so that's about meshes. Let's go back to our. Okay, so here are the mesh elements. A mesh has faces, and that's a subset of a 3D plane. Now, a 3D plane, by a 3D plane, I mean a 2D. A plane is always 2D, right? When I say a plane, I usually mean, in the geometric sense, I mean that it's a 2D surface. So when I say 3D plane, I'm short-circuiting my sentence and saying that a plane placed in a 3D environment. Okay, so I hope this should be clear to you. So when you hear a 3D plane, what should you understand? You should understand that it's a 2D entity. It's a 2D plane. A plane is always 2D, which is placed in a 3D space, 3D Euclidean space. So that should be clear. So it has facets, polygonal facets, edges, and vertices. And the topology of the mesh is captured by the underlying graph. All right. So that's the basic mesh, the idea behind a mesh. And usually it's a piecewise planar approximation. Like you can see here, two different types of meshes. The element types could be, I said triangular, quadrilateral, or in general polygonal. So here are two different representations of the same object, and I believe it's a CAD object. And you can see that the differences between when you represent the shape using a triangle-based tiling versus a quadrilateral-based tiling. So in a quad tiling, it's a quad mesh. Every element, facet element, is a quad, and if it's a regular mesh, the valence of every vertex in a quad mesh is exactly 4. Okay, let's first see what is regularity. Okay, so a regular mesh is one that has all regular vertices. So what is a regular vertex? A regular vertex in a triangle mesh is called regular if its valence is 6. So recall, what is the valence? Valence is the number of edges connected to a vertex. So for a triangle mesh, if I'm connecting a vertex with 6 edges, what does that mean? How many facets around that sharing that vertex? Who would answer that? 6, exactly 6, right? So exactly 6 facets connected to a vertex, then its valence, the valence of the vertex is 6, and that is for the interior vertices. Now a mesh may be closed or open. If it's a closed mesh, then all vertices of a regular mesh is if all vertices have the valence 6. But sometimes the meshes may be open. That is, they're not closed, they're not watertight. So for example, if I chop off part of a mesh, then it's an open mesh. And maybe, I can show you in Mesh Lab or something, some example of an open mesh. But if you have a boundary in a mesh, then it has then the triangles on the boundary, the vertices of belonging to the triangles on the boundary will have a valence of 4. The vertices that are on the incident on the boundary. So maybe do I need to draw something and maybe explain that? Maybe I can do that. That's already so let's say it's a 3D mesh like this, and it is open from here. This is the open part, and that's the interior. That's the interior. So valence is 6. Whereas if you have this, that's the boundary. Maybe I can draw the boundary in blue. That's the boundary of a mesh, of an open mesh. Remember, a closed mesh you will not find a boundary in a closed mesh. So that's the boundary. If we draw the triangles, a regular vertex is known as a vertex that has a valence of 4 on the boundary. Is it clear to all? Any questions? Right. So that's an open mesh. So a regular mesh is the one that has all regular vertices. Be the mesh closed or open, that doesn't matter. Therefore, the mesh, if you see at the top, looks like it is a regular mesh. Similarly, in quad meshes, the regular valences are for interior vertices, it is 4, and for boundary vertices or exterior vertices, it is 3. And I believe you can do it mentally as to how boundary in a quad mesh will look like. For interior, it is fine. You have 4 quads joined together, so you have 4 valence. But for the boundary, you have only 2 quads adjacent to each other. Therefore, the valence of a vertex, such a vertex, is 3. If you don't understand, let me know, but I hope this is clear. And vertices that are not regular are called irregular or extraordinary vertices. So it is in a mesh, it is not necessary that you have all regular vertices. It is pretty common to have meshes that have extraordinary vertices. Okay. So that's about surface meshes. And it's a surface mesh. So this tiling covers the boundary of the shape. There is nothing interior. There is nothing inside. Now, let's talk about data structures that we can use to build such a mesh. But I just recalled that maybe, I just talked about nothing being present inside. So I thought maybe I should clarify that point. And a connected concept is of a manifold. So maybe I can quickly talk about manifold as well. So there is a notion of a manifold mesh or a manifold surface versus a non-manifold surface. You may have heard this somewhere, but manifold versus non-manifold. What is the idea behind a manifold surface or a manifold? So we say a surface is two manifold, and that's a definition that should clarify that should clearly, anytime you're confused, if you just think about this definition, that's going to help you. So a two manifold is a surface that looks like a 2D plane, a Euclidean plane locally everywhere. So remember that example of the Earth, or that of an orange and an ant moving on an orange, for example. To the ant, it's a flat world, but we know that it's not flat. But if you go infinitesimally close to a point, for now thinking that the orange or the Earth is very smooth, it would look like a planar sheet. So, for example, if I draw this irregular surface, and then I see locally very close to, and I draw it in a different color. If I go very close to this point, then can I zoom in? No, I can't. If you see in a very small interval, this looks like a line. So locally, it's a line. And then if I go here, I can arbitrarily make the interval, the interval of investigation is as small as I want. So if you see that this bend, it doesn't look like a line, then you could make it even smaller, and then it would look like a line. So in this case, this is a one manifold, right? And similarly, a two manifold is one where you would find that infinitesimally very close to a point, you would see a plane always at all the points. Now, when would it not look like a 2D plane? So I'll just take this example of this one manifold, and I'm going to cross it out and make it a non-manifold. So if it has a structure like this, then you would notice that however close you go here, you will always find a T junction. The T junction will never go away, and it is the T junction that would make it not look like a line. So that breaks the manifoldedness of this shape. Similarly, how would a T look like on a surface? So let's say you have let's say you have a surface that looks like this, and then let's say you have another one that goes like this. So you have this surface, okay, and it is here that you would notice that at all the points at that edge, it's like a T locally, right? An extruded T, and that makes it a non-manifold. So yes, a mesh can have things inside that could make it non-manifold. And most of the times when we are talking about meshes, good meshes are always manifold. It's very difficult to make a non-manifold mesh a manifold because that's a challenging problem anyway. However, having said that, a mesh can always contain another component inside in a manifold fashion. So I may have a, for example, I may have a sphere. I may have an object here like this, and then another object like this. That doesn't make it non-manifold, right? It is when it touches it, so either an edge is shared, or it could be something like this. So it could be, let's say, a point here, a singularity that could make it non-manifold. So these are non-manifold. So this was just to tell you that a sheet of paper, if it's simple, that is, there are no T junctions or there are no common vertices like the one shown in this double cone example, it is most likely a manifold. So as long as it looks like a, topologically it looks like a plane, it qualifies for a two manifold. Now, some of you may have a question that, what if I have a cube? Is it a manifold or not? Who would tell me if is it a manifold or not? And then let me make it a mesh. So I will split the sides of this cube into triangles, and forgive my drawing. I'm making multiple strokes here just to beautify it. But who can tell me whether it's a manifold or not? It's a plain cube with 12 facets, triangular facets, connected in the usual connectivity of a cube. Who will tell me whether it's a manifold or not? Anyone here?
Yes, sir, it is manifold.
Okay, who thinks that it is not a manifold? It is okay to say that it is a non-manifold because you might say that, look, there are parts of this cube that go like this. So you have things like this. That's one triangle that I took here, and then that's a triangle that is not visible. So how about this edge? Is it a manifold? Is it a manifold edge or non-manifold edge? It's not a T, but does it look like a plane? Any thoughts?
A cube will have vertices, so it should not be two manifold, right? At least in my opinion.
Right.
So you're saying any non-differentiable portion should not be manifold.
Should not. So a cube like this is a non-manifold.
Yes.
Okay, that's not okay. Let me tell you. This is a very well valid two manifold. There is no doubt about it. Because when you talk about manifoldedness and non-manifoldedness, we are talking about the object in the topological sense, right? So this guy is equivalent to a sphere. So you, for once, you ignore the geometry and focus on the topology. the connectivity here, right? And I could, by some transformation, by some mapping F, I can transform this cube into a let me try to draw into a sphere that has this sort of connection, I could say. Let's say there are these 12 facets around, and then you would say that yes, now it looks like a manifold because then these creases are gone or at least minimized. So manifoldedness is a topological concept, and anytime you are confused, these creases don't count. So you don't differentiate. You don't say that it's not differentiable or it has C1 discontinuity, that is it's only C naught, that it is a manifold or non-manifold. No. So you don't decide based on the smoothness. You look at the topology. There are no T junctions. So so there are 2-3 cases of non-manifoldedness, and none of them appear here. And you can always map this cube. It's topologically equivalent to this sphere, to this sphere. So that's a manifold circle. Is it clear? Any questions?
So it will be useful to look at the homeomorphism to the object it is homeomorphic to.
Yes, that's right.
Okay.
Yeah, I don't want to get into the too much deep into it, but yeah, you should read more. I mean, those interested should look at more into these concepts of homomorphism and topology. But we just wanted to say that meshes could be non-manifold, and that is a problem. So we usually look at meshes that are two manifold.